Hello students! This lesson is on applications concerning right triangles. Page 1 is to solve the triangle. That simply means to find all the missing side and angle measurements. Let's begin with the missing angle. Here we have a right angle, so it's 90 degrees. Here we have 15 degrees. And since we know that the sum of the interior angles must be 180, we know that this angle plus this angle should equal 90 degrees. In other words, they are complementary. So this angle here should be 90 degrees minus 15 degrees, which is 75 degrees. And now we get to focus on the missing sides. Let's call the missing leg A and the missing hypotenuse C. Now before we go much further with this particular problem, let's pretend that this angle here was 30 degrees. That would make this angle up here 60 degrees, and this would be a 30, 60, 90 triangle. This is a special kind of triangle that we've already talked about. For such triangles, we know that the shorter leg, which is 5 inches, is half the length of the hypotenuse. So I could deduce right away that the hypotenuse would need to be 10 inches. And we know that the longer leg, which is A, is the shorter leg's length times radical 3. So we know that A would therefore be 5 times radical 3 inches. This is one way that we could solve a 30, 60, 90 triangle if I only know one of the three sides. However, this triangle is not a 30, 60, 90 triangle. So we're going to use technology and trigonometry to determine the values of A and C. And there are many ways to do this. I will show you several ways on this slide. Pick one of the two acute angles. I'll focus on the 15 degrees. Pick two sides. One is unknown and one is known. So we can pick side C and side 5 inches. Relative to 15 degrees, 5 inches is the opposite. And of course, C is the hypotenuse. Then ask yourself which trig function involves the ratio of sides of the opposite and hypotenuse. And there are two choices for this. One is the sine. So that the sine of the angle, and the angle is known, 15 degrees, is equal to the opposite over the hypotenuse. And the opposite is 5 inches. I'll leave the unit off. And the hypotenuse is C. This creates an equation. I can then solve for C and use a calculator to find sine of 15 degrees. I would need a calculator for that sine calculation because 15 degrees is not an angle for which the unit circle is useful. So if we shorten this equation and then multiply both sides of the equation by C, we would get C times the sine of 15 degrees is equal to 5. Keep in mind we're trying to solve for C, so I would divide next. C is equal to 5 divided by the sine of 15 degrees. At this point, I'm going to reach for a calculator and type in 5 divided by sine 15. Now you want to make sure that you are in degree mode, so I'm going to click the wrench in the top right and switch over to degree mode. And we get an answer of about 19.3. And that would be measured in inches. Now here are some alternate ways I could have set this problem up. There's another trig function that involves opposite and hypotenuse, and that would be the reciprocal of sine, which is cosecant. So we know that the cosecant of 15 degrees would be equal to the hypotenuse divided by the opposite. So that would be C divided by 5. Keep in mind that we're solving for C. So if I simply multiply both sides of this equation by 5, that will give me C isolated on the right. And we have 5 cosecant of 15 degrees is equal to C. This is another acceptable answer. Notice how this expression and this expression are the same, because cosecant is equal to 1 over sine. So 5 cosecant 15 degrees is really the same thing as 5 divided by sine of 15 degrees. And if you reach for a calculator, you'll confirm the same 19.3. Now relative to 15 degrees, A is the adjacent. So to find A, I can do a trig function that involves A, which is the adjacent, and 5, which is the opposite. Well, there are two different trig functions that come to mind. One is tangent, one is cotangent. Let's just pick one of those. We know that the tangent of 15 degrees would be the opposite divided by the adjacent, so that would be 5 divided by A. Now I'm trying to solve for A here. So I'm going to multiply A to both sides, and that will give me A tangent 15 degrees is 5, and now divide both sides by tangent 15 degrees, and then reach for the calculator. Again, make sure you're in degree mode, and we get about 18.66. That would be measured in inches. And now we have completed the triangle. We have solved it, meaning we have found all the missing side and angle measurements. I could have also found A using the cotangent function. I'll let you explore that option, knowing that cotangent is adjacent over opposite. Just to show you more variety, I could have found A and C using 75 degrees as my reference angle. But if that's the case, relative to 75 degrees, 5 inches would be the adjacent and A would be the opposite. So if I'm using the 75 degree measurement, let's go ahead and find the hypotenuse. So I want to use the hypotenuse and also a known value, so the adjacent. We need a trig function that involves hypotenuse and adjacent. Well, we can use cosine or secant for this. Let's use cosine. So we know that the cosine of 75 degrees would be equal to the adjacent divided by the hypotenuse. So that would be 5 inches divided by the hypotenuse, which is c. Keep in mind that we're trying to solve for c here. So I'm going to multiply c to the left side and then divide by cosine. Now keep in mind that the reciprocal of cosine is secant. So 1 over cosine of 75 degrees is the same thing as secant of 75 degrees. So I could freely just change this to 5 times the secant of 75 degrees, and then reach for a calculator. Again, make sure that you are in degree mode, and 5 times the secant of 75 degrees is about 19.3, or if I wanted to round to the 100th, 19.32. Notice that confirms what we got over here. Let's go ahead and change this to 19.32 as well. So we are seeing here that you could have found A and C using the 15 degrees as your reference angle, or you could have found both A and C using the 75 degrees as your reference angle, or some mixture of the two. Of course, another way to find a missing side of a right triangle, if you already know 2 of the sides, is the Pythagorean theorem. Let's say we find C first, which we did, and then we know that by the Pythagorean theorem, that leg squared, which is a squared, plus other leg squared, which is 5 squared, needs to be equal to c squared. But if we have found c, then I can substitute this expression for c into my equation and solve for a. And I will use this version for c, just so I don't have to write a fraction. C is 5 cosecant of 15 degrees, and that needs to be squared. Now I'm going to subtract 25 from both sides, and then take a square root, keep only the positive radical because a is a length, and then reach for a calculator. Make sure that you are in degree mode, and notice that the answer we get here in the third line equals the answer that we got in the first line, which are 2 different strategies for finding a, so about 18.66. So in summary, we could have used 15 degrees alone to find both a and c, or I could have used 75 degrees alone to find both a and c, or I could have done some sort of mixture. Or, as an option, I can use trigonometry to find a or c, and then use Pythagorean theorem to find the remaining side. So you have many different options when solving right triangles. Let's move on. Mark is standing on the top of a cliff that is 40 feet high. Bill is on the valley floor some distance away from the base of the cliff. Mark uses a theodolite, which is a measuring tool, to determine that the angle between looking straight ahead and looking at Bill is 20 degrees. Find 1, the distance between Mark and Bill, and 2, the distance between Bill and the base of the cliff. All right, so our cliff is represented by this leg of a right triangle. We know it's 40 feet high. Now let's simplify the problem by not considering the heights of Mark and Bill. In other words, let's just say that Mark is a singularity at the very top of the cliff. If we wanted to be more precise, we could measure how tall Mark is, but let's keep the problem a little simplified. Let's say that Bill is a singularity on the valley floor some distance from the base of the cliff. Now we're told that if Mark looks straight ahead and then looks down towards Bill, that sweeps out an angle whose measurement is 20 degrees. And our goal is to find how far apart are Bill and Mark, and how far is Bill from the base of the cliff. Since the first question is to find the distance between Mark and Bill, I'll call that one A, and the distance between Bill and the base of the cliff is the second question, so I'll call that B. Now we know the angle between the dotted line and the cliff is 90 degrees. So we know that this angle inside the triangle has to be complementary to the 20 degrees. So this interior angle has to be 70 degrees. And that's really the only angle I need to know in order to find both A and B. However, the other angle by Bill would also have to be complementary to 70 degrees, so it would have to be 20 degrees as well. But we're not going to use that information. I will use this angle alone and trigonometry alone to find both A and B. So relative to 70 degrees, I know that B is the opposite, the 40 feet is the adjacent, and the A is the hypotenuse. So I want to use a trig function that involves one known length and one unknown length. You would not want to use a trig function that involves both A and B, the hypotenuse and opposite, because they're both unknown currently. So I need to involve the adjacent. So let's do adjacent and hypotenuse first. The easiest one that comes to mind is cosine, although you could use secant. We know that the cosine of 70 degrees is equal to the adjacent, which is 40 feet, and I'll leave the unit off, divided by the hypotenuse, which is A. And we're solving for A. So I multiply A to the left side and then divide both sides by cosine. So A is equal to 40 divided by cosine. Make sure we're in degree mode and then reach for a calculator. And we get approximately 116.95. And this will be measured in feet. Now I could use the Pythagorean theorem now to help find B, but I'll use trigonometry again. And I'll use 70 degrees as my reference angle. I still want to involve the adjacent because the adjacent is an easier number to work with. It's simply 40. So I need a trig function that involves the adjacent and the opposite. Well, the tangent will work, and so will the cotangent. I would use cotangent just for variety. We know that the cotangent of 70 degrees, cotangent is adjacent divided by opposite, and the adjacent is 40 feet, and the opposite is b. Now multiply b to the both sides and then divide by cotangent, and we get that b therefore is equal to 40 divided by cotangent of 70 degrees. We could change this to 40 times tangent of 70 degrees because 1 over cotangent is the same thing as tangent. Either way, when I calculate this on a calculator, we get approximately 109.899, which will round to 109.90. And this answers both questions. Mark and Bill are 116.95 feet apart, and Bill is about 109.9 feet from the base of the cliff. Okay, let's go to the next page. Find the area of the triangle below. Now, a quick review on how to find the area of a triangle. Let's pretend that we have a right triangle to begin with, and the horizontal leg we'll say is B for base, and we'll say H for height, not hypotenuse. If you were to copy this triangle, flip it over, and put it on top of itself, you would see that it forms a rectangle. Well, the area of the triangle is exactly half the area of the rectangle, because two triangles make the rectangle. So if I can find the area of the rectangle and cut it in half, I will find the area of the triangle. So the area of the rectangle would have been base times height, just length times width, but then cut that in half. What if the triangle is not right? Then you're going to have to find out how tall the triangle is, perpendicular height from the base, and call that h. And if you want, you can break up the base into two parts, b1, b2, and then do what we did basically twice. Find the area of the left right triangle and the area of the right triangle and add them together. But it turns out that if you just simply combine the two bases into one and do the same formula we've already written, 1/2 base times height, we will get the area of this triangle, because base times height alone would give us the area of this rectangle, and the area of the orange triangle is exactly half the area of the entire rectangle. So both of these illustrations help us to recall that the area of a triangle is 1/2 base times the height. So this triangle here does not appear to be a right triangle. But if I draw a vertical line segment straight from the upper vertex, making a right angle with the base, then I can create two right triangles here. And now I can start using trigonometry to figure out all these missing sides and then ultimately find the area of the entire triangle. Now this 110 degrees needs to be split up into two different angles. I'll call them alpha and beta for now. But looking at the left-right triangle here, we know that alpha has to be complementary to 30 degrees. That means alpha has to be 60 degrees. That means beta has to be 50 degrees, so that together they form the original 110 degrees. Furthermore, looking at the right triangle that's on the right, this angle here has to be complementary to 50 degrees, so it must be 40 degrees. So we need to find the height of this triangle. We'll call that h for height, and then the entire base of the triangle. But we can do this by finding the two bases separately. We'll call them b1 and b2, and then we combine them to make the entire base. Now notice that this right triangle right here is a 30, 60, 90 triangle. So I can use trigonometry as the previous pages to find both h and b1, but I can also use what I know about 30, 60, 90 triangles. We know that the shorter leg, which would be h, which is opposite the 30 degrees, which is the smaller angle between 30 and 60, that this shorter leg here will be exactly half the length of the hypotenuse. So I know that h will be 4 meters. And b1 will be exactly 4 times radical 3 meters, which is approximately 6.93 meters. If I had used trigonometry as before to find b1, for example, I would have wanted to involve b1 and 8, and let's use 30 degrees as our reference angle. So b1 would be the adjacent and 8 would be the hypotenuse. Well, cosine involves adjacent and hypotenuse, so I would have said that the cosine of 30 degrees is equal to the b1, which is the adjacent, divided by the hypotenuse 8. Therefore, b1 would be 8 times the cosine of 30 degrees. Well, 30 degrees is an angle for which the unit circle is helpful. Looking at the unit circle, we track 30 degrees right here, and the cosine is the first coordinate. So radical 3 over 2 is the cosine of 30 degrees. And now I can do 8 divided by 2, and I confirm we get 4 radical 3 as an answer for b1. Or I could have reached for a calculator. However, the calculator won't give you this answer. It'll give you only a decimal version. And the calculator, make sure you're in degree mode, will confirm 6.93, approximately. So now I just need to find b2. I'm going to use this 40 degrees. Notice we don't know the length of the hypotenuse here. I don't need to know it because I know h. I know h, and I'm looking for b2, and I know this angle here. So relative to 40 degrees, h is the opposite, and b2 is the adjacent. So I'll use tangent for this part. tangent of 40 degrees will be equal to the opposite, which is h, which is 4, over the adjacent, which is b2, which I'm looking for. We'll multiply b2 to the other side and then divide both sides by tangent of 40 degrees. And then reach for a calculator. And we get about 4.77, and this will be measured in meters. So the entire base of the given triangle was the sum of b1 and b2. And if you want to be precise, do not use the rounded versions. So b will be found by doing b1, and b1 in exact form is 4 radical 3, plus, and b2 in exact form is 4 over tangent 40 degrees, which I could also write as 4 cotangent of 40 degrees. Keep in mind that 1 over tangent is the same thing as cotangent because they are reciprocals of each other. I'm choosing to write it this way so I don't have to write a fraction. And this is the best way to write b in exact form. Of course, it would be approximately 11.695, so about 11.70 meters. And now we know that the area, this is what we're after, of this overall triangle is 1/2 times the base times the height. Sticking with exact representations, we'd have 1/2 times, in parentheses, 4 rad 3 plus 4 cotangent 40 degrees, and then times the height, and the height was just 4. Now I can simplify 1/2 times 4 first and get 2, and then distribute the 2 through the parentheses. And so I could write my answer this way: 8 rad 3 plus 8 cotangent of 40 degrees. That gives us about 23.39. And this would be measured in meters squared, because the base was measured in meters, and the height was measured in meters. So we get square meters as a unit of area. There are times you want to leave your area in exact form, and then times where you may want to round it. Now, I do recommend that you avoid rounding until the final presentation of your answer. For example, I would not have wanted to use a rounded version of B1 and a rounded version of B2 to construct B, because then you start getting compound error. If your goal is to find the area, then avoid any rounding until you get to your final answer for area, and then you can round that answer if you'd like. All right, let's go to the next page. The graph of a circle is below. Find the coordinates of points P and Q. Let's focus on point P first. Notice the point on the far right of the circle is the point 3, 0. Well, that's 3 units from the origin, which is the center of the circle. Therefore, the radius of the circle is 3. That tells me the length of each of these dotted lines in the picture is 3 units. And that could be feet, inches, meters, unspecified. Now, if I make a right triangle by dropping a vertical from P down to the x-axis, then the coordinates of the point P will be the lengths of the 2 legs of this triangle, x and y. Also notice the angle is given without a degree symbol. That means you should interpret it as radians. And an angle whose measurement is 1 radian implies that this arc has the same length as 1 radius length. So this arc has length 3. That won't be useful information for this task, but it's helpful to remember what a radian means. We know that 1 radian is about 57 degrees. Let's use the angle 1 radian as our reference angle. Therefore, y is the opposite and x is the adjacent, and the hypotenuse is known. It's 3. So if I want to find x first, we know that the cosine of the angle 1 radian, don't put a degree symbol, is equal to the adjacent x divided by the hypotenuse 3. In other words, x is equal to 3 cosine of 1. I'll leave the parentheses off the 1. Similarly, we know that the sine of the angle is equal to the opposite, which is y, divided by the hypotenuse 3. And solving for y, we get y is equal to 3 sine 1. This time, when you reach for a calculator to find decimal representations, make sure that you are in radian mode when you type in 3 cosine 1. And when you do so, you get x is approximately 1.62, and that y is approximately 2.52. Therefore, the coordinates of P in approximate form is 1.62, 2.52. And these are approximate. If you wanted to leave it in exact form, you would write 3 cosine 1, 3 sine 1. Now let's focus on point Q. Again, I can make a right triangle by dropping a vertical straight down to point Q from the x-axis, and then finding these x and y coordinates, these legs. Now we know point Q is in the 3rd quadrant, so I know that the answers for x and y should both be negative. However, if I extract this right triangle and analyze it out of context, I know one interior angle is 20 degrees, and hypotenuse is 3. I can just do my regular trigonometry using 20 degrees as my reference angle, and say that the cosine of 20 degrees is equal to the adjacent, which is x, divided by the hypotenuse. So x is equal to 3 cosine 20 degrees, and the sine of 20 degrees is equal to the opposite, which is y, divided by the hypotenuse, 3. So y is equal to 3 sine 20 degrees. Make sure your calculator is in degree mode, and you get approximately, for both of these answers, 2.819, so approximately 2.82, and 1.026, so approximately 1.03. This is giving me positive numbers, but we know that the coordinates should both be negative since Q is in the third quadrant. So we can adjust them and conclude that point Q is approximately located at negative 2.82 and negative 1.03. And this answers our questions. There's another way to find the coordinates of point Q by using an angle that's in standard position. Now, standard position means we have to begin rotating from the positive x-axis. So if I begin with the positive x-axis and rotate all the way to a line segment that takes us to point Q, we have to figure out how many degrees that is. Well, halfway around the circle is 180, but then we have to go the extra 20. So this green rotation is 200 degrees. Or I could do a negative rotation and get there that way. So I'd be negative 90, and then I'd have to remove another 70, so negative 160. The green and the blue angle are both coterminal, and they're both in standard position. When using standard position angles instead, we can find the red x and the red y, so the coordinates for point Q, in the following way. We know that the cosine of this green angle, 200 degrees, will be equal to x divided by the hypotenuse, 3. So x will be equal to 3 cosine of 200 degrees. Now, if you plug this into a calculator, you'll get automatically the correct sign. So you get approximately negative 2.82. Similarly, the sine of 200 degrees will be equal to the opposite y divided by the hypotenuse, 3. And if I multiply the 3 over to the other side, we get y therefore is equal to 3 times the sine of 200 degrees. And this will give you the correct signed number automatically, because the 200 degrees is in standard position. So we get approximately negative 1.03. Now, the first way we did this, we used this 20-degree angle, and we were able to arrive at an answer via a sensible approach. But the 20-degree angle is not in standard position because neither of the line segments that form that angle are part of the positive x-axis. So we had to get answers that were both positive and then determine which ones needed to be switched to negative so that we would be in the correct quadrant. However, an approach moving forward, which I would recommend, is that you pick a standard angle, so either the green 200 or the blue negative 160. And I'll leave it to you to confirm that if I had done this approach right here, but using negative 160 degrees, that you would have got the same two answers. But using this approach, in angle measurements that are in standard position, that is measured from the positive x-axis, then you will automatically get the correct signs of the numbers for the x and the y coordinates. All right, and that concludes this lesson.